Thermodynamic Property Relations. This chapter discusses mathematical relations among thermodynamic properties that cannot all be measured directly. The main focus is how to derive relationships among properties such as T, P, V, U, H, and S using differential methods. This approach is essential to understand the behavior of real and ideal substances. These concepts form the foundation for advanced analysis of real gases, throttling processes, and entropy changes. The entire discussion relies heavily on calculus and partial derivatives. Lesson plan. Position of this chapter. This chapter comes after power cycles and refrigeration cycles and serves as a bridge to more advanced topics such as gas mixtures and chemical reactions. The material does not stand alone, but strengthens the understanding of energy, work, and heat concepts. Mastering property relations is essential before analyzing mixtures and complex systems. The lesson structure shows that this is a fundamental conceptual chapter. Without this understanding, many advanced equations become mere memorization. Learning outcomes. The learning outcomes emphasize the ability to systematically derive relationships among properties. Students are expected to understand and apply Maxwell relations and the Clapeyron equation. In addition, general relations for CV, CP, du, dH, and ds are key topics. The Joule-Thomson concept and the use of departure charts are also important components. All of these aim to make thermodynamic analysis more general and not solely dependent on tables. Function derivative. A function derivative describes how fast a quantity changes with respect to another variable. Geometrically, it is shown as the slope of the tangent line at a point. A small change in x produces a small change in f of x, expressed as delta f. This concept is the basis for understanding changes in thermodynamic properties. Without this, differential formulations in thermodynamics cannot be properly understood. Partial derivative. A partial derivative shows how one variable changes when only one independent variable is changed, while others are kept constant. In thermodynamics, almost all properties depend on more than one variable. Therefore, this concept is extremely important. Its geometric interpretation is the slope of a surface in a specific direction. This is the main language used to express thermodynamic property relations. Total derivative. The total derivative describes the change of a function when all independent variables change simultaneously. In the context of thermodynamic properties, this represents the actual change of the system. Mathematically, dz is a combination of contributions from each partial derivative. Physically, it represents the real change experienced by the system. This concept is crucial in deriving energy and entropy equations. The total derivative, dz, of a function z of x and y represents how z changes with small changes in both x and y, combining the effects of partial derivatives in both dimensions. Reciprocity relation in partial derivatives. The reciprocity relation shows that partial derivatives of two variables with respect to each other are inversely related. Mathematically, dz over dx at y multiplied by dx over dz at y equals 1. An implicit function example is used to prove this relationship. This concept is very important in manipulating thermodynamic equations. Many property equation transformations depend on this relation. Maxwell relations. Maxwell relations are four fundamental equations that connect partial derivatives of thermodynamic properties. These equations originate from the exact differential nature of thermodynamic potentials. Practically, these relations allow the calculation of hard-to-measure properties from easier ones. They are extremely powerful tools in engineering thermodynamics. Many property tables are implicitly built on these concepts. Slope of saturation curve. The saturation curve on a PT diagram shows the boundary between solid, liquid, and vapor phases. The slope of this curve, dP over dt at saturation conditions, has a very important physical meaning. This slope is directly related to latent heat and volume change between phases. This concept is the basis for deriving the Clapeyron equation. Without this understanding, phase change behavior cannot be analyzed quantitatively. The volume expansion coefficient, beta, expresses how sensitive a substance's volume is to temperature change at constant pressure. A substance with a large beta experiences a significant volume change, even for a small temperature increase. In contrast, a substance with a small beta shows very little volume change. This concept is important in fluid analysis, especially for liquids and nearly incompressible substances. Practically, it explains why some substances appear more responsive to heating than others. Correct answer. C. The substance expands significantly with a small temperature increase, showing greater sensitivity to heat. Explanation of incorrect options. A. The substance experiences negligible volume change with a small temperature increase. This is incorrect because a large beta indicates a significant volume change, not a negligible one, with small temperature increases. B. The substance contracts instead of expanding with increasing temperature. This is incorrect because a positive beta always corresponds to expansion, not contraction, with an increase in temperature. D. The substance's volume change is independent of temperature, regardless of the value of beta. This is incorrect, as beta directly relates to how volume changes with temperature, making it a crucial factor in determining temperature-dependent volume behavior. Temperature dependence of properties in ideal gases and incompressible substances. For ideal gases, internal energy and specific heats are functions of temperature only. A similar situation applies to incompressible substances, where energy changes are mainly determined by temperature changes. This simplifies the analysis because pressure and volume effects can often be neglected. With this assumption, energy change calculations become much more straightforward. This approach is widely used in thermal engineering. Throttling process. A throttling process is a flow process in which pressure drops significantly without producing work and with negligible heat transfer. In this process, the fluid temperature may increase, decrease, or remain unchanged depending on the substance and initial conditions. Thermodynamically, this process is characterized by constant enthalpy. This is highly relevant to expansion valves and refrigeration devices. This phenomenon cannot be understood using ideal gas assumptions alone. Throttling process, inlet-exit conditions, and TP diagram. A throttling process can be visualized on a TP diagram as a constant enthalpy line. The inlet condition is fixed, while the exit condition can be at various combinations of pressure and temperature along that line. This shows that pressure alone is not sufficient to determine the final state. The diagram helps explain why temperature can change in different directions. This graphical representation is very useful in real gas analysis. Inversion line and Joule-Thomson effect. The inversion line separates regions where the Joule-Thomson coefficient is positive and negative. On one side of this line, throttling causes cooling, while on the other side it causes heating. Each substance has its own characteristic inversion curve. The constant enthalpy lines show the actual process paths. This concept is very important in the design of gas liquefaction systems. In the Joule-Thomson effect, the inversion line separates regions where the Joule-Thomson coefficient, μJt, is positive or negative, indicating whether cooling or heating occurs during a throttling process. Constant enthalpy process and ideal gas. For an ideal gas, throttling does not cause any temperature change because enthalpy depends only on temperature. As a result, constant enthalpy lines coincide with constant temperature lines on a TP diagram. This explains why the Joule-Thomson effect does not exist for ideal gases. This behavior is very different from that of real gases. Therefore, throttling cooling is purely a real gas phenomenon. Enthalpy changes of real gases. For real gases, enthalpy changes can be evaluated using an alternative path that is easier to analyze. This path uses simpler reference states, such as near-zero pressure conditions. Physically, this does not change the final result because enthalpy is a state function. This approach is very practical in engineering calculations. This concept forms the basis for using enthalpy departure charts. Entropy change analysis of real gases is also often calculated using an alternative path, consisting of several simple steps. Reference points are chosen so that properties can be easily obtained from tables or charts. Even though the path is different, the entropy change remains the same because entropy is a state function. This approach simplifies the analysis without sacrificing accuracy. It is a standard technique in engineering thermodynamics.
Correct answer, B. The alternative path uses reference points with easily accessible states, making entropy evaluation more practical. Explanation of incorrect options. A. The alternative path avoids crossing constant pressure lines, simplifying entropy calculations. This is incorrect because the alternative path does cross constant pressure lines, P1, P2, P0, to help track entropy changes effectively. C. The alternative path accounts for the actual process path's irregularities by ignoring real gas behavior. This is incorrect because the alternative path is designed to simplify calculations, not to ignore real gas behavior. It approximates the entropy change without oversimplifying. D. The alternative path eliminates the need for considering pressure changes, focusing only on temperature effects. This is incorrect because the alternative path considers both temperature and pressure changes, using reference states to facilitate entropy evaluation.
References are from Eunice A. Chengel, Michael A. Bowles, and Mehmet Kanoglu, Thermodynamics, an Engineering Approach, McGraw-Hill Education.